In previous lectures, we learned about poise estimator, say x bar, about a population parameter mu. Now, today we would like to talk about hypotheses and tests to infer some properties about mu. So here are some very intuitive examples. The first one is we would like to test the fairness of a coin. A person wanted to check if a coin was fair, then he tossed the coin 20 times and got 13 heads. Then, is it evidence that the coin is not fair? Or is it evidence that the coin is fair? So that's the first intuitive example we want to know. The second is, suppose to test a manufacturing procedure. 500 items it produced were randomly sampled, and 34 of them turned to be defective. And can we say that the procedure has a defective rate lower than 10%? Okay, so where does the 10% come from? Because 34 of them are defective, then 34 divided by 500, right? So it's a little bit less than 10%. Right? However, due to some variations, it may exist. So we would like to know whether the parameter proportion P, okay, is less than 10%, while my P hat is 34 over 500. The third example, a machine at a Coke production plant is designed to fill bottles with 16 ounces of Coke, and the actual amount varies slightly from bottle to bottle. From past experience, it is known that the standard deviation of the amount is 0.2 ounces. A random sample of 100 bottles filled by the machine has a mean of 15.96 ounces per bottle. Is there evidence that the machine needs to be recalibrated? Okay, so that is to say, people claim that the machine would fill bottle 16 ounces. However, after measurement of 100 bottles, the mean is only like 15.96. And then, based on the 1596, can we say that the claim that the bottle can be filled 16 ounces by the machine is correct? So here, our sample mean is 15.96, and we would like to know whether the population mean is equal to 16 or is not equal to 16. So here's our interest. And each of the above problems involves a certain claim about a population, okay, about a population. So either it is about the population parameter P or the population parameter mu. So in example 1 and 2, right, it is a claim about P, and in example 3, it is a claim about mu. So a statistical hypothesis is a claim about a population, whether it is about a single parameter, like in our example 1, 2, 3, right? Or the values of several parameters, or the form of an entire probability distribution. And a hypothesis test is an assessment of the evidence provided by a data set in favor of or against a hypothesis about a population. And in the hypothesis test, we want to decide if the observed value, okay, where the observed value can be either sample mean, sample median, or any kind of observed value of a specific sample statistic is consistent with the hypothesis on the corresponding population parameter. That is to say, if my observed value is consistent or has very little difference from the hypothesis value, then most likely my hypothesis is correct. The sample statistic is thus referred to as a test statistic. So my test statistic can be x, right? Can be either x or x tilde or something like xi minus x, something like this. So any statistic derived from sample can be a potential test statistic. And if the observed value of the test statistic and the hypothesis value of the parameter differ a lot, okay, we need to assess whether the difference is due to an incorrect hypothesis or is merely due to chance of variation. The null hypothesis, we usually denote it as H0, is the claim that is initially assumed to be true, and the alternative hypothesis, denoted by HA, is the assertion that is contradictory to H0. So, for example, still we use the three examples at the beginning. For each problem, the corresponding hypothesis can be formulated as follows. So in first example where we toss a coin, right, and we would like to decide if this coin is fair or not, then my hypothesis is the coin is fair, which means the probability of landing on heads is 1/2. And the alternative hypothesis can be the coin is not fair, which will result in the alternative hypothesis, the probability of landing on the heads is not 1/2. And another reasonable alternative hypothesis can be the probability greater than 1/2. So why can we call it a reasonable hypothesis? Why can we call it a reasonable alternative hypothesis? Because recall 13 of them, right, lands on head and out of 20 trials. So this will result in a probability less than 1/2. So it is reasonable to set our alternative hypothesis to be the true probability of landing on heads is greater than 1/2. And in the second example, we would like to see whether the defective rate is truly 0.1. And because we have 34 defective out of 500, and it is less than 10%, right? So that is why a reasonable hypothesis, null hypothesis, should be the probability of defective rate is less than 0.1. Another reasonable null alternative hypothesis could be that the probability is not equal to 0.1. And the third example, we want to test whether the filled amount is 16 ounces or not. And mu is the mean of the amount of coke filled by the machine. Now, an alternative hypothesis can be mu is not equal to 16. And because our observed value is 15.96, then another reasonable alternative hypothesis can be the HA, the mu less than 16. And from the hypothesis, okay, two possible conclusions can be drawn. The first is we can reject H0. Okay, we reject H0 when our observed value differs significantly from hypothesis value. And we do not reject H0 when the observed value does not differ too much from the hypothesis value. And let's introduce general procedure for hypothesis testing. And before devising any test procedure, so first of all, you need to formulate H0 and HA carefully, and this is the most important step of a scientific investigation. So H0 is the statement being tested, and in this course, it typically states a plausible value of the parameter under investigation. For example, theta equals theta 0, with the implication that the inconsistency between the observation and the hypothesized value is only due to chance variation. And in the Koch example, our H0 is mu equals 16. So 16 is our hypothesis value. And the hypothesis value theta 0 is referred to as the null value. So 16 is the null value. And HA is the statement we will favor if we find evidence that H0 is false. That is to say, if the observed value differs a lot from what we hypothesized, then there's evidence, right, that H0 is false. And it usually states that there is a real inconsistency between the observation and the hypothesized value of the parameter. And in the Koch example, HA can be mu not equal to 16, or mu equal or greater than 16, or mu less than 16. And HA is two-sided if it has the form theta not equal to theta 0. So that is to say, this is a two-sided. And HA is one-sided if it has the following form. That is to say, both of these tests, they are one-sided. And after we formulate H0 and HA, a test procedure is specified by the following. First procedure is we need to find a test statistic. So a test statistic is a function of the sample data on which the decision is to be based, and it should provide a measure of the difference between the observed data and what would be expected, right? So for example, if our hypothesis value is mu equals 16, and what we observed is x bar equal to 15. So our test statistic should be based on the difference between 16 and 15. And then we measure this value to see if this value is big enough to claim that the hypothesis value is inconsistent with my observed value. And the second is, after we determine a test statistic, the second is to determine a rejection region. Rejection region is the set of all test statistic values for which x0, h0 will be rejected. And h0 will be rejected if and only if the observed or computed test statistic value falls in the rejection region. And the following outcomes are possible when conducting a test. So when the reality is H0 is true, you have two possible test results. The first test result is that you accept H0. When the truth is H0 and you accept H0, then there's no error, right? So you made a correct decision. However, if the reality is H0, but you reject H0, so it will incur a type 1 error. And similarly, if your reality is HA, but you accept H0, it will incur a type 2 error. And when your reality is HA and your test result in favor of HA, then you made a correct decision. So this table is very important. And for a real-world problem, it is very rare that an error-free procedure is available. Okay, and instead we should seek procedures that have very small probabilities of errors. And traditionally, we use alpha to denote type 1 error and beta to denote type 2 error, where type 1 error is where the probability of type 1 error is the probability of rejecting H0 when H0 is true. So this statement is type 1 error. And this statement is type 2 error. So type 2 error is not to reject H0 when actually your HA is true. and 1 minus, and most ideally, right, in most ideal situation, we would want alpha to be small and beta to be small, right? Similarly, if we want beta to be small, then we would like 1 minus beta to be big, and 1 minus beta is often referred to as the power of the test. So this is a very important concept. That is to say, when your type 2 error is very small, right? When your type 2 error is very small, then it means that the test is very powerful. And for a specific test on a H0 versus HA, okay? Because H0 already specifies a unique value of theta, so there is a unique value of alpha. However, HA does not specify a unique value, right? It specifies infinite possible values of theta, right? Look at HA. HA can be theta is not equal to theta 0. That means there are infinite possibilities of theta. And that is to say, there is a different value of beta, which is the type 2 error for each value of theta that is included in HA. So in the coin toss example, the null hypothesis is probability is equal to 1/2, okay, where the probability is the probability that the coin lands on head. And we consider because our 13 divided by 20, this is a little bit greater than 1/2. So we put the null hypothesis like this, the probability is greater than 1/2. And the test statistic is the number of heads in the 20 tosses, right? So in our situation, a realized value of x will be 13. And suppose one sets the rejection region as the following. That is to say, when my number of heads is greater than 13 or equal to 13, then I reject the hypothesis that my coin is fair. Okay, so this is one possible rejection region, right? Now, based on this rejection region, okay, rejection region, so our rejection region is 13, 14, 15, all the way to 20. So suppose this is my rejection region, then how powerful will my test be? And how much mistake will my result be, okay? And now, suppose H0 is true. H0 is true means that the probability is 0.5. Then it means that x will follow a binomial distribution with parameters 20 and 0.5. Then let's evaluate alpha. Alpha is the probability of type 1 error. And a type 1 error it means H0 is rejected when H0 is true. So that is to say, what it means that when H0 is rejected, because our rejection region is from 13 to 20. So that is to say, when my observed x is greater or equal to 13, then my H0 is rejected. So here is the situation. So x greater than 13 means x0 is rejected. And when H0 is true, it means that x follows binomial distribution with parameters 20 and 0.5. So we would like to examine the probability that x is greater or equal to 13 when your x follows binomial distribution with parameters 20 and 0.5. So this is easy to do, right? So this is just a very typical question we met in Chapter 3 or Chapter 2. When your x follows binomial distribution 20.5, so what is the probability that x is greater or equal to 13? Right? So we can get it from calculator. Right? Get it from calculator. So that is to say, this probability is the probability that x is less or equal to 1 minus x is less or equal to 12. And we can get this from calculator. and just use 1 minus the probability x is less or equal to 12, then we have the probability x greater or equal to 13 when x follows 20 binomial distribution 20.5. And the result is 0.132. That is to say, when my H0 is true, okay, when my coin is really fair, then I still have a chances to reject my H0. Okay, I still have a chance to reject my 0, which is 0.132. So that's all about alpha. Now let's talk about beta. So in contrast to alpha, there's not a single beta, and instead there's a different beta for each different value that falls in H0. So for example, falls in HA, right? So HA is P greater than 1/2. Now 0.6 falls in this region, right? So let's say if our P is 0.6, then what is my type 2 error? So type 2 error, what is the probability of my type 2 error? So beta usually denotes the probability of type 2 error, and type 2 error is x is not rejected when my HA is true. Okay, when my HA is true, then what is the probability that I do not reject my H0? And now suppose that my HA is 0.6, okay? Then not rejected means x is less or equal to 12. So this statement can be translated into this mathematical statement. So that is to say, we would like to, the type 2 error is to evaluate, the type 2 error when P equals 0.6 is to evaluate the probability when x is less or equal to 12 when x follows binomial distribution with parameters 20 and 0.6. And this gives us a probability 0.584. So that is to say, if my coin is not fair, and if the P is actually 0.6 rather than 0.5, then roughly 58% of all experiments consisting of 20 tosses of the coin would result in the test incorrectly not rejecting H0. So that is to say, this type 2 error is pretty high, right? So when my alternative hypothesis is true, this test is not very powerful to detect it, okay? Even though the even though my alternative is true, I still have over 50% probability to accept my H0 instead of rejecting H0. So this type 2 error is pretty high. So in the above example, we formulate how to calculate a type 1 error, type 2 error based on a specific region. Now, suppose that instead of setting the rejection region like this, okay? Previously, my rejection region is from 13 to 20. That is to say, whenever my heads, okay, whenever the number of heads is greater or equal to 13, then I reject that this coin is fair. Now, another person sets the rejection region differently, okay? If we set the rejection region differently, say this, okay? So this time, we reject the null hypothesis if my heads are greater or equal to 15. Now, comparing to the previous rejection region, this one obviously makes it harder to reject H0, right? Because I have to be over 15 to reject H0. And consequently, the probability of type 1 error should decrease, while the probability of type 2 error should increase. That is to say, again, following the procedures above, right? The alpha is the probability of type 1 error, where type 1 error is to reject H0 when H0 is true. And when H0 is true, it means X follows binomial distribution with parameters 20 and 0.5. And to reject it, it means that X should be greater or equal to 15 based on the new rejection region. Now, this gives us a probability of 0.221. So that is to say, my type 1 error is very, very small. That is to say, and when my H0 is true, it is very, very rare that my test statistic will reject it. And now let's evaluate the type 2 error. So type 2 error, okay, type 2 error. So still we use the probability 0.6. Suppose that type 2 error is the so probability of type 2 error is denoted by beta, and type 2 error means X0 is not rejected when your P is equal to 0.6, and remember H0 is P equal to 0.5. And not reject H0 means X is greater or less or equal to 14. And when P is equal to 0.6, it means that X follows a binomial distribution with parameters 20 and 0.6. Now, after some calculation, it gives us a 0.874. So this is much greater than the 0.5 we calculated before in the previous example using a different rejection region, right? So this calculation confirms that when my rejection region shrinks, then my type 1 error will be decreased and my type 2 error will be largely increased, right? This is even an even higher type 2 error. Now, for the Coke example, assume the amount of Coke in a bottle has a normal distribution. Then the distribution of the amount of Coke in a bottle filled by the particular machine is we assume to be normal distribution with mu and sigma square. And here, sigma is known to us. The null hypothesis, is mu equal to 16. And the alternative hypothesis is mu not equals 16. And now if X bar is the sample mean of a random sample of 100 bottles filled by the machine, then X bar has the distribution, right? So this is a very old knowledge, right? So that is to say when X1, X2, Xn follows, now we have 100, right? So this n will be equal to 100. So all of them will follow mu sigma square. Then the average out of the 100 samples will follow mu and sigma squared divided by 100. So we learned that before, right? You can derive it again to make yourself more familiarized with it. Suppose here my rejection region is, my rejection region, okay? That is to say, when the observed value and the hypothesis value's difference is greater than 0.0392. So suppose that this is my rejection region. Now, what is my type 1 error? Okay, so what is my type 1 error? Again, type 1 error is the probability, type 1 error is to reject H0 when H0 is true. And when H0 is true, it means that my X bar, and when H0 is true, it means that mu is equals 16. When mu equals 16, then X bar will follow 16. And sigma square divided by 100. That is to say, and that will give us, right? And because my rejection region is this, so reject alpha. Okay, and we already calculate the rejection region, which is this, right? So actually, we only need to evaluate this probability when we know the X bar follows normal distribution. And this is a very typical calculation problem, okay? And we utilize the properties of normal distribution, and still from calculator, we can get values. So that is to say, my type 1 error is 0.05. And on the other hand, if my mu is 15.97, that is to say, my mu is not equal to 16, right? And this mu falls into HA, right? So that is to say, where my H0 is not true. So what is my type 2 error? So what is my type 2 error? So my type 2 error is the probability that you do not reject H0 when your, so there should be an X bar here. The probability you do not reject H0 when your H0 is not true, right? So now, on the other hand, if my mu is equal to 15.97, then my X bar will follow a normal distribution with mean 15.97 and a variance equals 0.02 square. And do not reject H0 means X bar falls between this, right? And a final calculation gives us a type 2 error equals 0.677. Now, if we set a different rejection region, okay, so all of the calculation is based on this rejection region before. Now, if we change our rejection region a little bit, we change the criteria, okay? We set the rejection region to be if the difference of the observed value and the hypothesis value is greater than 0.05152, then we reject null hypothesis. And this will result in a smaller alpha, smaller type 1 error, right? So this type 1 error is 0.01. And it's very similar to the fair coin example before. As your type 1 error decreases, then your type 2 error will increase. And using the same statement, just by modifying the rejection region a little bit, we are able to get a new type 2 error. So the examples illustrate an important fact about hypothesis testing. That is to say, one has to make a trade-off between the probability of type 1 errors and the probability of type 2 errors, which is the trade-off between alpha and beta. Supposing an experiment and a sample size are fixed, and a test statistic is chosen, then decreasing the rejected region results in a smaller value of alpha, while a larger value of beta for any particular parameter value consistent with HA. The standard approach to type 1 error and type 2 error is as follows. So the first is to specify the largest value of alpha that can be tolerated. So this value is often referred to as the significance level of the test. So traditionally, levels of significance are either 0.1, 0.05, or 0.01. And the second is identify a rejection region such that the alpha is no greater than the significance level and has the value of beta as small as possible, or equivalently is as powerful as possible. Okay, that is to say, okay, if we would like a type 1 error to be no greater than 0.01, then this rejection region will be out, right? Because this rejection region gives us a type 1 error 0.05, right? So in order to have a type 1 error 0.01, right, or even less, so we have to set this kind of rejection region, okay? And test about a population mean. And suppose the unknown mu of a population is of interest, and suppose the null hypothesis mu is equal to mu0 needs to be tested. And depending on the problem at hand, and there are three kind of alternative hypothesis we can specify. Okay, the first is mu is greater than mu 0. The second is mu is less than mu 0. And the third is mu is not equal to mu 0. And to test the hypothesis, we let mu hat be an unbiased point estimator of mu. And the idea is to examine how different this unbiased estimator is from the hypothesis that value mu 0. And a suitable test statistic is the z-score we learned before. Okay, so here this mu hat is our unbiased point estimator for mu. So it can be x bar, right? It can be x bar. And this mu 0 is what we hypothesized value. Like in the Coke example, mu 0 is equal to 16, right? And sigma mu hat is the standard error of mu hat. And if the standard error of mu hat is not known, then we use estimated standard error of mu hat. So what is standard error of mu hat? Okay, standard error of mu hat is sigma divided by square root of n, right? And if sigma is not known, okay, if sigma is not known, we usually use s to replace it. So that will result in an estimated standard error of mu hat, which gives us s divided by square root of n, where s is equal to the square root of 1 over n minus 1 times summation of squares. And next, we need to identify the rejection region for the test statistic. And for the first alternative hypothesis, the rejection should have this form, right? Right. So that is to say, whenever h0 is whenever your observed value is too bigger than a constant c, then we should reject h0 and accept ha, right? And for the second type, now alternative hypothesis, that is to say my HA is mu less than mu 0, then my rejection region should be a range that is less than the constant c. That is to say, when my observed value is less than something, right, then we can have confidence that the H0 is not true and HA is true. And the third type of alternative hypothesis is mu is not equal to mu 0. So that is to say, when the absolute value of my observed value is greater than something, then we say that this mu is not true. Or we say that mu is not mu 0. So here we look at some concrete example. So for example, now we have normal population with known sigma square, and let x bar be the mean of a random sample of size n from normal mu sigma square. Then mu hat equals x bar is a unbiased estimator of mu, and the corresponding z statistic is as follows. And if h0 is true, okay, if h0 is true, h0 is true means that z follows normal distribution. Normal distribution with a zero standard normal distribution. And for HA, mu greater than mu 0, then the probability that So here it is the probability of type 1 error, right? So we reject, so when my HA is like this, so my rejection region should take this form, right? So this is my rejection region, and this is when x0 is true. So this statement is the statement of type 1 error. So the probability of type 1 error will be this, right? So which will result in 1 minus phi c, where this phi is the CDF of normal 0, 1. And to achieve a significance level alpha, we need to set this equals alpha. So that is to say, C will equals Z alpha. And when you have a different alternative hypothesis, then similar statement can be derived, right? And for HA, which is mu not equals mu 0, then your type 1 error will be this. Your probability of type 1 error will be this. And in order to achieve a significance level alpha, then you have to set your phi c to be alpha over 2. So your C will result in this. And to summarize, we call it a z-test. Let x bar be the observed mean value of a sample of size n from normal distribution with sigma known to us, and we let the following statistic to be our test statistic. And our test H0, mu equals mu 0 at a significance level alpha, then the rejection region is the following. When your HA is mu greater than mu 0, and you should reject the hypothesis if your observed mean is greater than this quantity. And similarly, if your alternative hypothesis is this, then you should reject the null hypothesis when your observed value x bar is less or equal to this quantity. And when your alternative hypothesis is mu not equals mu 0, then you should reject null hypothesis when the absolute difference of the x bar and mu 0 is greater or equal to this quantity. And here is an example. Okay, for the Koch example, we have mu 0 equals 16, which is our hypothesis value, and we have sigma equals 0.2, this is what we know, and n equals 100. And we observed that x bar is equals to 15.96. Then we can calculate this z value, right, by plugging in all of the known number, and this gives us a number -2. And if we would like to test a H0 versus HA of this form, then my z alpha over 2 will be, when my alpha is 0.05, then my z alpha over 2 will be 1.96, right? And that is to say, my z, the absolute value of z is 2, and this is greater than alpha 0.2. So we can reject the null hypothesis at significance level 0.05. Okay. However, if we make our significance a little bit smaller, okay, then my z alpha over 2 will be 2.58. And because my observed value 2 is less than this critical value 2.58, then we don't reject H0.